In last lecture, we were talking about fast Fourier transform, particularly decimation in time radix to FFT algorithm. In this lecture, we will be focusing on decimation in frequency radix to FFT algorithm. Okay, so that is the focus of this lecture. Okay, let's get started. Okay, so as usual, we are going to write the expression for DFT. We are always going to start with the same expression. So x of k will be n equals as usual 0 to n minus 1, x of n w n k to the base n. Whatever might be the algorithm, we always start with the basic expression of DFT. Okay, now we are going to collect the first n by 2 terms separately and next n by 2 terms separately. Unlike the even and odd samples, we are going to collect the first n by 2 separately and second n by 2 terms separately. Okay, so these are the first n by 2 terms, and the limits for the second will be n by 2 to n minus 1, x of n w n k to the base n. Okay, now let this be term 1, let it be term 2. Okay, so we want to actually combine term 1 and term 2. So for that, we have to take term 2 and we have to change the limits. Only if we change the limits to the same limits as term 1, say 0 to n by 2 minus 1, we can combine term 1 and term 2. Okay. Fine. How will you change term 2's limits? The limits originally are from n by 2 to n minus 1. So x of n, this is term 2. I am writing it again one more time. Okay. Now, how do we change the limits to 0 to n by 2 minus 1? Put m equals n minus n by 2. Okay. So we have to write everything in terms of m now. So the summation limits will become m equals 0 to n by 2 minus 1. How? N minus 1 minus n by 2. Is that clear? Okay. So we have the limits. Now we have to write everything in terms of m. So m plus n by 2. N is nothing but m plus n by 2, and then w, again m instead of n, we are going to write it as m plus n by 2 k to the base n. So we have changed the limits for the second term, and you can actually replace m by n here because it doesn't make any difference. It's just a variable. Okay. So I'm going to write both the terms again. The first term will be as usual n equals 0 to n by 2 minus 1, x of n w n k to the base n plus again the limits are going to be n equals 0 to n by 2 minus 1 x of n plus n by 2 w n plus n by 2 k to the base n. Okay, the first term will remain as such. Now we have to do some simplification in the second term. So I am writing the second term alone. Again, n equals 0 to n by 2 minus 1. Okay, x of n plus n by 2 w n k to the base n into what? W n by 2 k to the base n. Now what is this w n by 2 k to the base n? E power minus j 2 pi n by 2 k divided by n. So ultimately it's going to become what? N and n gets cancelled, 2 gets cancelled, e power minus j pi k, which will be nothing but minus 1 the whole power. Okay, I am rewriting both term 1 and term 2. You can also do it along with me. Okay, w n k to the base n and the plus n equals 0 to n by 2 minus 1 x of n plus n by 2 into w n k to the base n minus 1 the whole power k. Okay, now if I have to combine, I have to take x of 2k separately and x of 2k plus 1 separately, right? Okay, so I am going to write the first term as usual, n by 2 minus 1 x of n w n into 2k to the base n plus n equals 0 to n by 2 minus 1 x of n plus n by 2 into w what? W n into 2k. I am just replacing k by 2k. Minus 1 the whole power 2k will become 1. So that is how I am able to combine two terms here. Okay. So, okay. The limits will be this, and then you will have x of n plus x of n plus n by 2 the whole w or 2nk to the base n. Now what is w2nk to the base n? We have seen it in DIT also. So that will be nothing but wnk to the base n by 2. Okay. So you are going to get something like this. So this will be the expression for x of 2k. Now let us introduce a new signal, say a of n. let it be x of n plus x of n plus n by 2. So ultimately this expression will become a of. Okay, now we will concentrate on the odd terms, x of 2k plus 1. So minus 1 the whole power 2k plus 1 will be minus 1. So you have a difference here rather than summation x of n w n into 2k plus 1 to the base n plus n equals 0 to n by 2 minus 1 x of n plus n by 2 w n 2k plus 1 into what? Minus 1 the whole power 2k plus 1. So it will be minus 1. Fine. So it will become the expression, I can write it as 0 to n by 2 minus 1 x of n w 2nk to the base n. I am doing it stepwise. W n to the base n minus n equals 0 to n by 2 minus 1 x of n plus n by 2 into w 2nk to the base n w n to the base n. That's it, right? Okay. So as usual, w2nk to the base n will become wnk to the base n by 2. So we get something like x of n minus x of n plus n by 2. We are going to multiply this by w n n. Then finally w n k to the base n by 2. So again we are going to introduce another signal d of n. So ultimately x of 2k plus 1 will be d of, because this is n by 2 point DFT. Now as usual, let us consider only 8 point DFT right now. So a of n and b of n now contains 4 points each, right? So we have to continue the splitting. As usual, we start by writing the expression for a of k. A of k contains how many points? N by 2 points. Okay, so n equals 0 to n by 2 minus 1 a of n w n k to the base n by 2. As usual, we are going to collect first n by 4 terms separately and second n by 4 terms separately. Okay, so we have the first term like this, wnk to the base n by 2. As usual, second term will have the limits n equals n by 4 to n by 2 minus 1 a of n w n k to the base n by 2. Okay, Same as before, we have to change the limits for term 2 to combine term 1 and term 2. So as usual, put m equals n minus n by 4. Okay. So ultimately the second term will become, limits will change from 0 to m equals 0 to n by 4 minus 1. So we have to rewrite everything in terms of m. So a of m plus n by 4, because n is m plus n by 4. W m plus n by 4 k to the base n by 2. Okay. I am writing the expressions again. Actually, we are more bothered about the second term. First term will remain as such. The second term would be n equals 0 to n by 4 minus 1. A of n plus n by 4. I have replaced m with n. And as usual, w nk to the base n by 2 minus 1 the whole power k. Refer to the previous derivation. Okay, like how we collected x of 2k, here we are going to collect a of 2k separately, a of 2k plus 1 separately. Okay, so for a of 2k, this will be the expression n 2k to the base n by 2 plus n equals 0 to n by 4 minus 1 a of n plus n by 4 into w n 2k to the base n by 2 into minus 1 the whole power 2k will become 1. Okay, so let us combine and we will get n equals 0 to n by 4 minus 1 a of n plus a of n plus n by 4 the whole into w n k to the base n by 4, because w2n k to the base n by 2 will be wn k to the base n by 4. So I am introducing again a new signal d1 of n. Okay, so ultimately a1 of a of 2k becomes d1 of k. Okay. Similarly, we can write a of 2k plus 1 like how we did before for x of 2k plus 1. So I am going to write it directly. N equals 0 to n by 4 minus 1 a of n minus a of n plus n by 4 the whole into w n n by 2 into w n k to the base n by 4. Now another new signal is introduced. Let it be D2 of. So A of 2k plus 1 will be D2 of k. Okay. The same way we are going to split B of k also. So I hope you people are familiar with the derivation right now. So B of 2k will be what? N equals VO2 n by 4 minus 1 V of n plus V of n plus n by 4 the whole into W n k to the base n by 4. Now again a new signal D3 of n is introduced. Okay, so D of 2k becomes D3 of. What about V of 2k plus 1? I think you got the idea right now. Okay, so n equals 0 to n by 4 minus 1. V of n minus V of n plus n by 4 into W n by 2 W n k to the base n by 4. Okay, let us say that this is D4 of n. So ultimately this will become D4 of k. Now D1 of n, D2 of n, D3 and D4 of n contains 2 points each. So stop splitting and start computing. Okay. Now let us collect the time domain expressions separately and frequency domain expressions separately. This will help us to draw the butterfly diagram, and it will also help us to get the overall picture of the decimation and frequency radix 2 algorithm. Okay. So in this case example we have taken n equals 8. So we will be considering only 3 stages. Okay, like in DIT you will have 3 stages of butterfly diagram. Okay, so we are consolidating the time domain expressions here. We are already aware of that. So A of n equals x of n plus x of n plus n by 2, B of n x of n minus x of n plus n by 2, the whole into Wn. Similarly you have D1 of n, D2 of n. I hope you can understand. N by 2, D3 of n will be what? B of n plus B of n plus n by 4. Then finally D4 of n will be what? B of n minus B of n plus n by 4 the whole into W n n by 2. Okay, so these are the time domain expressions. Shall we start writing the frequency domain expression? What are the frequency domain expressions? A of k is nothing but x of 2k. Do you remember? And B of k is nothing but odd samples of capital X of k, that is x of 2k plus 1. So that is why we have decimation frequency. D1 of k will be what? D1 of k will be A of 2k. D2 of A will be, D2 of k will be A of 2k plus 1. d3 of k will be what? d of 2k, and finally d4 of k is nothing but d of 2k plus 1. This is for n equals 8. I already mentioned that. So 3 stages are involved. In DIT we have a of n equals x of 2n and w of n equals x of 2n plus 1. So that is why it is called as decimation in time. But on the other hand, if you have a of k equals x of 2k, then we are talking about decimation in frequency. Okay, now in case of decimation in time algorithm, the first stage itself is computation of 2-point DFT. Okay, but in decimation in frequency, the 2-point DFT computation happens at the last stage. Okay, so this is one of the basic difference between our DIT and DIF. Okay, now let us try to get the overall picture of the DIF algorithm. So we have already the time domain and frequency domain expressions written down. So the first thing is you have to compute, this is the first stage, you have to compute a of n and b of n from x of n. So this will be the first stage. Okay, what will be the second stage? Computing d1 of n and d2 of n from a of n, and d3 of n and d4 of n from b of n. Remember guys, we are talking about computations. Okay, so the final stage, third stage, will be simply 2-point DFT computations, because d1, d2, d3, d4 contains 2 points each. So you have 3 stages in this example because n equals 8. So the final stage will be computation of 2-point DFT. Please note the difference that in DIT we don't compute d1, d2, d3, d4. We simply rearrange x of n to get d1, d2, d3, d4 of n. Okay. Now after obtaining the FFT of d1, d2, d3, d4, we obtain capital D1 of k, d2, d3, d4 of k, which itself are the outputs in the bit reversed order. Okay, so actually d1, d2, d3, d4 constitutes x of k. Okay, so shall we start drawing the butterfly diagram for 8-point radix to decimation in frequency? Okay, I think we'll proceed. We have to have some patience here. Okay, so the first stage, what will be the first stage in case of radix to DIF? You have to compute a of n and b of n from x of n. Okay, and second stage will be computing d1, d2, d3, d4 of n from a of n and b of n, and the final stage will be taking 2-point DFT of d1 of n, d2 of n, d3 of n and d4 of n to obtain capital D1 of k, d2 of k, d3 of k, d4 of k, which itself is the output in bit reversed order. Okay, so here in case of DIF, the input is given in sequential order. In decimation and time, the input was given in bit reversed order. Here we are giving input in sequential order. Okay, so as I mentioned before, our 2-point DFT will be the last stage in decimation frequency algorithm. So let us start drawing the butterfly diagram. So input is given in sequential order. So I am writing x of 0, x of 1, etc. up to x of 7. Right? Okay. Now after the first stage, what are the outputs you will obtain? What outputs you will obtain after the first stage? A of n and B of n, right? Okay, so A of n and B of n will contain 4 points each. So A of 0, A of 1, A of 2 and A of 3, and we will also get B of 0, B of 1, B of 2 and B of 3. Okay, after the second stage, what are the outputs? We will get D1 of n, D2 of n, D3 and D4 of n. So each contains 2 points, right? So D1 I am writing D1 of 0, D1 of 1, D2 of 0, D2 of 1, D3 of 0, D3 of 1, D4 of 0, D4 of 1. Okay, and the final stage obviously will give the 2-point DFT of D1, D2, D3, D4 of n, which will be D1 of k, D2 of k, D3 and D4 of k. So capital D1 of 0, D1 of 1, capital D2 of 0, D2 of n, capital D3 of 0, D3 of 1, then capital D4 of 0, D4 of n, D4 of 1, sorry. So these D1 of k, D2 of k, D3 and D4 of k are themselves output in the jumbled fashion or reverse fashion. Okay, now let us check the time domain expressions to draw the butterfly diagram. You have to remember all these things. Okay, now what is A of 0? A of 0 will be x of 0 plus x of 4. You have to see please refer to the time domain expressions, you will understand how. Okay, so similarly A of 1 will be x of 1 plus x of 5. That is A of n is nothing but x of n plus x of n plus n by 2. Similarly, A of 2 will be x of 2 plus x of 6. Now A of 3 will be x of 3 plus x of 7. Is that clear? Okay. Now what will be the B of n expression? Do you remember? B of n is x of n minus x of n plus n by 2 into w n n. So for D of 0 you'll have the drill factor W08 coming into picture, and sorry, it's a freehand drawing, so that is why I have drawn certain things beforehand. Okay, so ultimately what I'm trying to convey is D of 0 will be x of 0 minus W08 x of 4. D of 1 will be x of 1 minus W18 x of 5, and so on. Do you understand? Okay, now shall we go to the next stage? What is d1 of n equal to? d1 of n is nothing but a of n plus a of n plus n by 4. So d1 of 0 will be a of 0 plus a of 2. d1 of 1 equals a of 1 plus a of 3. Similarly, what is d2 of 0? For d2 of 0 and d2 of 1, it involves trivial factors, because d2 of n equals a of n minus a of n plus n by 4 into wn n by 2. Okay, so please refer to the time domain expressions one more time if you have any questions. Okay, so d2 of 0 is a of 0 minus w08 a of 2. Similarly, d2 of 1 is nothing but a of 1 minus w14 a of 3. The same way, actually we can start drawing for d3 of 0 and d3 of 1. d3 of n will be b of n plus b of n plus n by 4. So d3 of 0 will be b of 0 plus b of 2. d3 of 1 will be b of 1 plus b of 3. d4 of n will be what? b of n minus b of n plus n by 4 into w n by 2. So you'll have trivial factors coming into picture. So d4 of 0 is b of 0 minus w04 b of 2. Okay. So similarly, d4 of 1 will be b of 1 minus w14 b of 2. Okay, so we'll come to the final stage. Though 2-point DFT involves just addition of 2 points and subtraction of 2 points, for pattern we are going to draw like this. Okay, so capital D1 of 0 will be small d1 of 0 plus d1 of 1. Capital D1 of 1 will be small d1 of 0 minus d1 of 1. This trivial factor W08 is 1. Okay, so we are going to do the same thing. Fine. So d3 of 0 is d3 of 0 plus d3 of 1. d3 of 1 is d3 of 0 minus w08 d3 of 1. Actually, this w08 we put only for pattern. Okay. Uh, so in case of decimation and frequency, the input is supplied in sequential order. As I mentioned earlier, capital D1 of k, D2 of k, D3, D4 of k themselves are the outputs in bit reversed order. Refer DIT lecture for what is it, the proof. Okay. Now, as usual, we have to bring all the twiddle factors in terms of base twiddle factors. So, n equals 8 here again. So, what are the base twiddle factors? How many base twiddle factors will you have? N by 2. And the base twiddle factors are W08, 18, 28 and 38. So, I am going to replace all the twiddle factors by in terms of base twiddle factors. Okay. So, wherever we have W04, we write it as W08. W14 we will write it as W28. Do you remember? W2nk to the base n is equal to Wnk to the base n by 2. So, W1 to the base 4 will be nothing but W2 to the base 8. So, we write everything in terms of base twiddle factors, and we have almost completed the butterfly diagram. Okay. So, the last step is to draw the basic butterfly of decimation and frequency, and investigate the hardware requirements for the fast Fourier transform. Let us now look at the basic pattern involved in the decimation and frequency radix 2 algorithm. So, if you take any 2 points, say x1, x2, the pattern inherent is capital X1 will be x1 plus x2, capital X2 will be small x1 minus W Rn x2. Okay, so this is going to be the pattern which is going to repeat itself in DIF algorithm radix 2. Okay, so finally we have to investigate the hardware requirements for fast Fourier transform. Let it be DIT or DIF, the hardware requirements do not change. Okay, now for one butterfly, that is a basic butterfly what we have drawn. Okay, how many complex multiplications and additions are required, guys? How many complex multiplications and how many complex additions are required for getting x1, one complex addition? For getting x2, you need to perform one complex multiplication plus one complex addition. So, for one butterfly, you'll have 2 complex additions and 1 complex multiplication. Okay, now say if we have n points, n point FFT, then how many stages will you have? Radix 2 algorithm will have log n to the base 2 stages. For example, when n was 8, the number of stages were 3. Okay, now how many butterflies are there in each stage? Each stage contains n by 2 butterflies. The same example can be used for n equals 8. For every stage you will have n by 2, that is 4 butterflies coming into picture. Okay, so the total number of butterflies needed for endpoint FFT is R n by 2 log n to the base 2. Now, how many complex additions and how many complex multiplications are needed for computing endpoint FFT? See, for one butterfly, we need two complex additions. Okay, so how many butterflies are there? N by 2 log n to the base 2 butterflies are there. So that into 2 will be the number of complex additions. So that will be n log n to the base 2. Okay, and similarly for number of complex multiplication, for each butterfly you need one complex multiplication. So the number of multipliers needed, complex multiplication needed is n by 2 log n to the base 2. This concludes the decimation frequency radix 2 algorithm.